At this very moment, I would ask my colleague Kodruts to check if we can do the live stream. Anyways, everyone is very welcome to this third episode of our webinar series, which is aimed to, so our webinar series is aimed to discuss the main intervention fields of our SPIRE Biomass project. And as you can see in this very quick slide, SPIRE is a smart post-industrial regenerative ecosystems, is a nature-based solution experimental project that has been financed by the European Union and the European Commission through the Urban Innovative Actions. And the SPIRE project aims at reclaiming heavy metal contaminated sites in a former Romanian mining capital through the phytoremediation, nature-based solutions, and ecosystem services. And in particular, one of the key fields of experimentation will be focused on the upcycling of vegetal biomass and in the production of green energy and construction materials. And so today's webinar will explore circular ecosystems for sustainable cities, discussing new frontiers of biomass upcycling. And we're extremely glad to have a very special panel of speakers from Spain and the United States. We have Paul Merino from Onyx Barcelona, Tim Falk from the State University of New York College of Environmental Science and Forestry, and Alison Mers from the Healthy Material Lab at the Parsons School of Design. And then we will also have, as a discussant, Amaya Celaya Hernandez, which is the Urban Innovative Action expert. So I will just give you a brief introduction. Paul Merino is the managing director of Onyx. He has a background in biotechnologies, and since 2015 is leading the industrialization of Onyx, which is an industrial biotech startup from Barcelona that transforms industrial waste into new sustainable materials. They're implementing a growth strategy following the circular economy principles and based on finding synergies with local industries. And Paul will discuss upcycling paper mill waste into construction materials. After Paul, we will have Tim Falk, who is a senior research associate at the State University of New York College of Environmental Science and Forestry in Syracuse, New York, USA. He has over 20 years of experience working in the fields of forestry, agroforestry, short rotation woody crops, bioenergy, and phytoremediation. And he is responsible for a series of research projects focused on the development of shrub willow biomass cropping systems as a feedstock for bioproducts and bioenergy. Is also actively involved in research and development of sustainability assessment of bioenergy systems, life cycle assessments of willow biomass crops, and woody biomass from forests. So, and then Tim's presentation will focus on the WILLOW project that he carries out at SUNY, and he will discuss about energy and other application of Salix viminalis. And then, last but absolutely not least, we have Alison Mers, who is a AI lead AP architect, associate professor of architecture, and the co-founder and director of the Healthy Materials Lab at Parsons School of Design in New York. She is the co-principal investigator of the Healthy Affordable Materials Project, which is a multi-year grant funded by JPB Foundation. The project is a coalition of 4 organizations who work together to incorporate human health as criteria for evaluating building products to improve the interior environments of affordable housing. And finally, Amaya Celaya Alvarez is an architect, urban designer, and master NOHA in international cooperation and humanitarian action. She is an urban resilience senior expert for both the United Nations and the European Commission, and she is currently working as the urban innovative action expert on our project in Biomass. So without any further ado, it is my pleasure to leave the floor to Paul Merino with his presentation on upcycling paper mill waste into construction materials. Paul, the floor is yours.
Thank you, Pietro. Thanks a lot for inviting us to participate in this webinar. As you well explained in the beginning, we at Onyx, we're an industrial startup that was born in Barcelona, and we are specialized in developing process to recover cellulose waste. If you can move on to the next slide, please. I'd like to start with why we do it before telling you what we do and how. And that's pretty simple. The constructions material industry, it's fully linear. Most of the time, in most of the cases, it takes raw materials. That means we eat mountains. We then mix it with all sorts of chemicals, some of which have toxic emissions, to generate a product with amazing technical specifications. But with a very short lifespan. At the end of it, it has to go to a landfill. If we can move on to the next one, please. So at the very end, and you can go quickly through this and the next one, we are eating mountains and forests, we are destroying them to, can you move to the next one? To end up, to fill up landfills. In Europe, as an average, each citizen generates 1.87 tons of construction waste a year. And that in the construction itself, it generates 1/3, if you can go to the next one, Pietro, 1/3 of all waste in the globe. To our understanding, that's totally unsustainable in the long term, and that's the main reason why we generated, why we started with Honext. Can you move on 2 more? This one and this one. Yep. Honext, what we do is pretty simple. We manufacture a material made out of 100% waste and ensuring during the process, analyzing everything that we add to it to ensure its recyclability at the very end of its use. If we take a look at the process in detail, that what you can see in this picture is our raw material. It's called paper mill sludge. If you're not familiar with it, it's like paper mills. They normally now take recovered paper, transform it through their water-based process and make new paper out of it. But there is an important percentage of fiber, roughly 10%, it depends a bit on the type of paper that is manufactured, that it's too damaged to make new paper. So it stays with the processed water, and from time to time, they send it to the water treatment station, and before sending it there, they remove it. They remove this bad fiber together with other process additives. And the main uses right now of this waste are 2. They either burn it to generate thermal power, but it's not efficient at all to start with because this waste has around 50% water content. So the first thermal power that we need is to evaporate this water. And the second main use of it is to dispose of it on a landfill. That's a lot, especially because in Europe we generate around 7 million tons a year of this waste. So what we do first when we receive this waste in our factory is we analyze its composition, the type of fiber that it has. It can be, depending on the origin, a chemical or mechanical fiber, how damaged it is, how short the fiber is, as well as how dirty it is. At the very end, what our process does, the first step, is to mix this fiber with some other waste fiber, normally recovered cardboard, to ensure that we have let's call a standard composition of fiber independently of the origin of the different waste. I mean, this waste, when it comes from a paper mill, it's stable most of the times, but when we take 2 or 3 different sources, 2 or 3 different paper mills, it varies significantly. So we add what we call our stable fiber, that's recovered paper mill, to ensure that at the very end the mixture is the same. Can you move on to the next one, Pietro? Thanks. That's once we have this waste characterized, what we do is we add a cocktail of enzymes that what it does is to clean this fiber and maximize its ability to link with other fibers. Cellulose fiber, it's an organic compound that has the natural ability to link with another fiber through hydrogen bonds. So the way we designed our process was, instead of having to add resins to generate a strong material, let's maximize the amount of bonds that each fiber can make, so we also get a healthy material without compromising its sustainability. That's why we use the enzymes to prepare the fiber. Once the fiber is ready, then we undergo a mechanical transformation. If you can go to the next slide. We have a solution of cellulose, of now standard, clean, and ready to link cellulose fibers in water. It's with a percentage between 3 to 5% of cellulose in the water dilution, and we have to shape it in boards. That requires a mechanical separation of the fiber from the water, and we do it through pressure and positive pressure as well as vacuum technology. And at the very end, we have what is a wet board, has around 50 to 60% water content that we need to dry in a drying tunnel. This is one of the trickiest parts of our process. Cellulose, as it links together, it links to other fibers when you extract water, especially during the drying phase. So if the way we extract water is not homogeneous along all the thickness of the board, the fibers start to link with other fibers in an heterogeneous way, and thus the board bends. Therefore, we have to have a pretty smooth drying process to achieve a board at the very end that has a perfect flatness. And to summarize a bit what the process, the key of it is that we don't need any resins. And we just use 100% of waste fiber together with enzymes and water, pressure and heat to generate a new material. The no need for resins, first of all, contributes into having healthy environments. Other materials, especially wood-based materials, they use urea formol resins that they have emissions of volatile organic compounds. One of them is formaldehyde, which has been proven to be to provoke cancer in human beings. So, especially in the spaces nowadays that we've improved construction to be much more efficient and insulated from a thermal point of view, that's critical to have inner spaces without volatile compounds on the air. But also the resins, as we explained before, they contribute. But a resin does not allow most of the times to recover a material, to recycle it, and that's why we use none. If we can move to the next one. That till now it's our product that's and process how we do it, but we developed that in a laboratory and in a pilot plant within the university. But when we had to scale it up to industrial scale, we thought that it's not just the product that needs to be sustainable, but the whole business model itself. So our first question was where to set up a factory. Where can we put a factory with the lowest environmental impact possible? And we decided to put it in a landfill. That is a factory, it's placed in a landfill where all the utilities, all the process utilities that we consume, this is the gas, the electricity, as well as the water, come from waste. And in terms of water, we have a water treatment station, so everything that we consume at the very end is cleaned up again and comes back to our process. If we can move to the next one, thanks. These are a rough summary of the properties of the material. If we can skip this one and the next one, we can go into detail, but it meets all the technical specifications needed for its application as an internal board in internal partition in construction. But if we have to highlight some of them, first of all, and of course, it's the sustainability of the material. We are Cradle to Cradle Silver certified. We aim to achieve gold level in the next renewal. Secondly, is that not just we don't have emissions, but that we also improve a lot the acoustics of the inner spaces. If we can move to the next one, Pietro. That's a comparison of the material sound absorption capacity as a material, not as a final product, compared to normal partitioning materials. So we generate much comfortable internal spaces. That's mainly the main reason behind that is our material, thanks as we use the natural bonds between cellulose fibers, we have a fibrous material, and therefore it has a much higher capacity to absorb or to reduce the sound than any other material that it's at the very end, a block of resin with something inside. And finally, reaction to fire. This, from us, it's very important to highlight because using waste, sometimes waste has, in our case, has fiber, but it also has other inorganic compounds that are used in the paper production process. We could see this as a disadvantage because at the very end it impacts or really it limits our mechanical strength, but it also gives us a very good reaction to fire. Without adding any additives, our material is a Class C reaction to fire. That allows us to be in most of the construction projects in Europe, and well, now we're working to achieve a Class B, that it's the maximum we can reach with a bio-based material without adding toxic or really chemical compounds. Finally, as a market, it's to to us, we target MDF. Clearly, it's a really complicated market. MDF, in terms of technical properties, it's an amazing material, but that's it. And it's in terms of sustainability, and it's a completely linear economy material. So in Europe, so you have a rough idea, we consume 16 million cubic meters a year of MDF, of which 2.5 are consumed in construction. And our factory right now has a capacity of 2,000 cubic meters a year. We do believe we have a lot to improve in terms of materials. All sustainable materials, or at least the way we see it, we start with the disadvantages, and it is that we cannot use as many additives as MDF would use to improve the properties, but there are many options available. It's a matter of trial and error and improving. And we do see a lot of potential to end up replacing this type of fiberboards. Here you'll see some of the projects, of the last projects we've done. As I said before, it's a material for internal partitions in construction. It can be transformed as any fiberboard using the same sanding, cutting machines. That's not a problem. Obviously, it's slightly different as it has no resins. Sometimes it behaves slightly different, so it's just a matter of small adaptations on the transformation processes. On these ones, Pietro, we can go fast. Those are the last projects we finalized, the co-working, where it was used as an internal partition with some shapes in order to improve the sound comfort. And also a museum exhibition in Barcelona, where the material, it was digitally, can you stop here for a second? It was digitally printed on top of it. And I wanted to stop in this picture because, as all new or all innovation, we have a lot to improve. And here you can see that, for instance, our surface is not perfect yet. It's something that we are working on, but it's not a flat surface. It has some irregularities, some holes, and so on. To our clients we have two types of clients from us. From one side, architects and designers. They love that. They actually, when they use a sustainable material, a material made from waste, they want to show that. And this, to them, it's a proof of that. From the other side, though, we have the industrials, the carpenters, industrial carpenters, and so on. For them, it's slightly more difficult because they are used to having perfect materials. But at the very end, it's a matter of being with them, supporting them on the transformation, on the first transformation process, and all the fear is gone. That's again the same. And as I said before, we not just want to have a sustainable product, a product that is recyclable and has no emissions, but also we think on how to generate the maximum or the best environmental impact on all decisions we take. And this starts, this is completely based on collaboration. We do believe that the way to grow is to collaborate with paper mills, who nowadays have a problem with their waste because they make huge volumes and they're paying for it, for something that is transported to a landfill. On the other hand, they have an amazing operational knowledge. So what we want to do, and what we've done with the first factory, is we set up our production line within this industrial, they manage it, and then we manage the market. But we manage the market in a way that what is produced, for instance, in Germany, it's consumed also in the national market, because it makes no sense from one side to transport waste to landfills or long distances, but it doesn't also make much sense to such products that at the very end, they are not super special, have to travel, for instance, from South America to Europe, because transport has a huge environmental impact. So we size the technology in a way that it's profitable from an economical point of view, with somehow limited as small capacities, and we aim at implementing it locally all over Europe. If we can go to the next one, this, as I was saying, that's the interior of our factory in Spain. We built it in the landfill together with with a waste management company, the Grignot Group, and they are actually, we are collaborating in the operation of it. Because that's what we think. I mean, it makes no sense to destroy mountains to fill up landfills. We need to achieve a future where landfills become mines, because there are lots of waste that can be reused in there. And also, and I think the current situation even highlights it more, where things are made locally, or let's say in a regional point of view, to avoid the impact of transport that is huge on the environment. Can we go to the next one? This is a short summary. First of all, we are also, we've been funded by the European Commission as within the Horizon 2020 program. It has helped us a lot because they funded us the startup of the factory, as well as the initial market introduction. This has allowed us to really focus on what makes a lot of, on what brings value in the mid and long term, not just focus on the short term. And well, we are also supported by some important groups, especially in the construction sector here in Spain. And well, that's about it. If you have any questions, I'm more than happy to answer. Thank you.
So we are in. Thank you very much, Paul. That was really interesting, seeing how from ideas you can really make a difference. And that was an interesting point on the difference and the need to match between the coolness, the hype that new materials generate for the designers, and all the technical feasibility problems that are faced by and the difficulties that are faced by the carpenters, and all of those that are actually called to practically use the materials. And I think this is going to be a real challenge. And I will keep this as an item of discussion for later. But now I'm very happy to move to Syracuse, New York, and give the floor to Timothy Falk from the SUNY Center for Sustainable and Renewable Energy, who will talk about the WILLOW project, energy and other applications of Salix. So Tim, floor is yours, please.
Great, thank you very much. Glad to be here. Thanks for the invitation to come and share with you. We'll go to the next slide. So what I'm going to do this morning is I'm going to talk through a project that we've been working on for a number of years, to give you an example of how we've been using WILLOW in one situation to do remediation on a former industrial site, and then to use that material, harvest some of that biomass and use it for energy applications in the end. So just a comment on this, that there's a number of partners. So through this whole process, we've been involved with a number of partners. So Honeywell International is our main partner. They're the ones that currently own this site. They weren't the ones that were involved for this 100 years. What we're dealing with here are really settling basins where they disposed of waste over about 100 years, where they were making soda ash. So it was a logical place to do it here because we had salt brine resources, we had a lot of limestone, so a lot of the raw materials, and lots of water. So what you see here in this image on the left, these two white areas, actually along the western edge of this lake are also settling basins. We're not dealing with those because they're being used for other areas. So we have about 280 hectares here of settling basins that have been sitting there and really not being used for anything. And so this partnership with Honeywell, a couple of consulting firms in town, a number of different levels in the community, both from the local community that lives around this settling basin, these settling basins, through to the county and then the state level regulators. We've all worked together over a number of years to develop this project and to make it happen. So that's been an important part of the success of this, is the collaboration that's occurred over time and listening to one another and adjusting as we go along. So the main environmental impact associated with this area is the leaching of chloride salts into a stream that then runs into Onondaga Lake here. Okay, so we're not necessarily dealing with heavy metals in this situation, but what we're dealing with a very high salt concentration material, and that has negative impacts on the environment and on the lake. We'll go to the next slide. So one of the things when we started this is we wanted to look at a sustainable reuse remedy. And so finding an alternative way to address the problems on the settling basins here And the real goal was to reduce this leaching of salts. So the mandate from the regulatory agency was to protect human health and the environment. That's the way it's phrased here in New York State. And so that's what was needed. What we really wanted to do here was to take a more sustainable approach to remediation of this site. So this picture here on the left is a document developed by the federal government, our Environmental Protection Agency, on ideas on how to make remediation projects more sustainable. So we drew on some of that. New York State has also since come out with some guidelines that are similar to those in terms of how to reduce the impacts from remediation processes. What we're really doing here on this site is minimizing leaching out of the site. So the way we're doing that is managing the above ground and the immediate soil surface. So we're increasing evapotranspiration, so pump off more water and increase the water holding capacity of the soil, right? And that way you can pump off the water with the willow as opposed to having it leach down through the system. Okay, next slide, please. So here's an image of some of the harshest areas up here on these settling basins. So when I first visited these sites 12, 13 years ago, this is what I was introduced to. Now, it's not all quite like this. There are some areas with vegetation, but this is the most extreme. So this had been 20 years since they had last deposited material in this site, and there is nothing there. So that just gives you an idea of the sort of environment that we're dealing with to make this work, right? It's high salt concentration, it's high pH, it's low nutrients. There's no textural structure to this soil to work with. It's very challenging. We employ what we refer to, actually what colleagues that I work with have developed and referred to as a phased remediation strategy. So we work through a series of steps in incremental steps to try and make this work, and then kept adapting and modifying as we went along. So I'm going to walk you through a few of those steps, and then we'll talk about end use applications when we get to the end. Okay, so why willow? Well, there's a number of attributes about shrub willow that make it appealing. It's not the only species, but for what we wanted to do in the package that was trying to be created, it had the right attributes. So it's a pioneer species that works well and grows naturally on disturbed sites. So it's used to dealing with harsh, unpredictable conditions. It's easily propagated from woody cuttings, so it's easy to scale up and multiply fairly easily. Willow has high transpiration rate. So some people might say it's an inefficient user of water, and that's true. It uses more water per kilogram of wood that it produces than most other woody species. In this environment, it's exactly what we want. We want it to pump off more water. You can harvest it, you can cut it down, take the biomass away and use it, and we'll talk about that at the end of the presentation, and it will just sprout back. And so once you plant it, you can manage it in a 3 or 4 year harvest cycle and have it keep sprouting back. You don't have to replant it, and it's relatively easy to manage. Huge genetic diversity in willow. There's over 300 species of willow around the world, and we had been working on willow here at the university and with some other colleagues for 10 or 15 years already, and so had a fair amount of experience in terms of what its potential opportunities might be. There was also history of willow being used in this region for basket making industry. This was the heart of the willow basket making industry at the early 1900s. And so you can still find those willows across the landscape if you go out and look for them. Okay, next slide. So here's greenhouse screening. This is where we start. So the first thing we do is we go out and we were looking at the site. We took some samples, we did some testing, we collected some material. The picture on the left is a screening trial where we took 40 different cultivars of willow and put it in straight solvay waste. We put it in an amended, so some organic matter in with the solvay waste, and then a control, a perlite mixture of control. Out of that, we found that there was 10 superior cultivars that seemed to do fairly well in a greenhouse setting. So that we've learned that lesson. Then it's clear that we're going to have to do something about amending the site. The things are not going to grow on this kind of site. And so we started looking at organic matter. And so one of the goals here was to find local organic waste sources, material that was being sent to landfills, and find out, could we make use of that material and incorporate it back into the site as an organic amendment? So this trial on the right is where we tested a series of different organic materials. We had organic materials from a local brewery, from a pharmaceutical company, from the wastewater treatment plant, and from another company that had a biosolids that was producing. And so we tried these different mixtures in the greenhouse to first get an idea of what might work. The best one was from this pharmaceutical company, and it really worked well. And unfortunately, a few years later, that company decided to move their the production process to another location. So we lost that source material, but you adapt and move on. So next slide, please. So the next thing was go to the field. So remember, I told you we had these 10 cultivars that we identified. So this picture at the bottom, you can see this block, right, with different squares in it. So there's the 10 cultivars from the greenhouse trial put out into the field in a trial there. It's fairly clear there that some things are not working, right? So it's important to follow this through the process. What works in the greenhouse in a controlled environment is wonderful. And we eliminated 30 varieties that probably weren't going to work in the field. But if we go to the next slide, I'll just show you some data that this did not work so well in the field for some of these varieties. So you can see this one I have circled called SV1. That actually produced the best in the greenhouse. By the second rotation, it was totally dead. So, you learn lessons as you go along. So SV1 did well in a greenhouse environment, was controlled and watered regularly. You put it out in a real environment where rainfall is sporadic and you have dry periods and other pests that may be an issue, and it didn't do well at all. However, there are a number of varieties. That green bar is the sort of yields and biomass production we get on good mineral sites in the area. And so we've got a number of varieties that are growing just as well as they do on mineral soils in the area. So that's success. We can move forward to the next stage. Next slide. So the next thing was to go out and figure out this organic amendments question. And so we take that greenhouse trial, and here's another trial we go out, and we put out blocks of different amendments. Lots of interesting stories around this, around working with the community and the timing of it and their concerns about odors and lots of issues like that. And so it took lots and lots of interaction to even get to this stage and to make this work. But we put this trial out and we learned some lessons, and it allowed us to make some recommendations then to begin the commercial scale up, larger scale up of this material. So if we go to the next slide. So here it is. You can see in that picture on the right, that green plot on the left is this organic amendment trial that I just showed you. So that's where we did that testing with there were 8 different organic amendment treatments in there, plus a control. Then we go across the road there, and we tackle this very challenging site that I showed you at the area. So at the beginning, this is this area where there's virtually no vegetation. The company challenged us, Honeywell challenged us and said, look, if you guys can make it work there, we'll believe you, right? And then we'll talk about expanding it to other areas. So that's where we started. And you can see that there's 2 different colors being mixed in here. This sort of brown, dark brown, and a dark material. So we're still testing 2 different organic materials out here because we're not entirely resolved. There's a couple of things, which one works the best? They both seem to have potential. And then there's issues about supply down the road. So if we're going to scale this up over a couple hundred hectares, having some flexibility in your organic waste material that you're going to use is beneficial, because maybe the facilities that are there are not going to be there. They're not going to produce as much as consistently over time. And so we wanted to maintain those options. In the end, we've actually modified in the last few years, and we've started actually mixing in horse manure. There's a fair amount of, for recreational purposes, horses maintained in the central New York area. So there's a lot of horse manure. There's a company that started collecting that and mixing it with the brewery, the waste from the brewery that we were already using. And so that's the material we've been using for the last few years. Lots of lessons learned about how do you incorporate this material into this, into these settling basins. This is very challenging material to work with. When it gets wet, you can lose equipment. Literally, it'll sink up to the bottom of the equipment when the material is wet, just because there's no structure. And so lots of challenges and lessons learned. If we go on to the next one. So where are we at now? We've now installed the first 40 hectares of this WILLOW ET cover, and you can see a picture of that here. This is what is called one of the settling basins. There are several more. There's another 140 hectares of area that could be, this could be applied to. We are currently in the process of going through a regulatory review with the state agency for them to determine whether this is an acceptable solution to the problem or not. We're still learning. Those plots out there, we're out collecting data to try and optimize willow health and willow growth, and now using UAVs to try and do that at the scale of area that we have now. Go to the next slide. So we've done other things, right? There's lots of things we've looked at. We've looked at, well, here's greenhouse gas emissions. And so clearly big benefits to be had here. So what you have here on this scale on the y-axis is global warming impact in kilograms of CO2 per hectare of land where you put a remediation practice in. And you have the WILLOW ET cover versus a typical clay cover or a geosynthetic cover. That green line through the WILLOW ET cover shows you that the WILLOW cover actually has a negative carbon footprint over a 30-year period. So it's taking up more CO2 than you're expending in the use of fossil fuels to run harvesters or planters or material to spread organic matter and all those other emissions. So it's actually got a negative footprint versus very large footprints. So there's big benefits to be had here. And we're now here in New York State at a point where we're going to start in 2021. The state will start requiring an accounting of carbon benefits and put a dollar value on it. So this is going to be important when regulatory agencies start looking at these kind of processes and make these kind of decisions. The other thing we do on this site, as I've mentioned, is we harvest it off. So every 3 years we harvest it off. I'll just mention there's a lot of other benefits. We've done work on biodiversity and soil benefits and lots of other things that are associated with this. So there's lots of other things that are being added in terms of added values. But let's talk, if you go to the next slide, so about biomass production. So the way the system is designed is we don't just plant and walk away. We plant it and we're going to manage it like an energy crop, which we do on hundreds of other hectares here in the central New York region. So here we are harvesting this biomass. So you can see the size of the material. You harvest it off. This machine cuts it and chips it. This is a forage harvester that you'd cut corn silage or grass silage with. And so what do we do? So now we're at this question of we've started harvesting this biomass off and how do we make use of this? So we're producing chips and there's various options, right? We can use chips directly in heating applications, combined heat and power, or just in electricity. So right now there's a company in upstate New York that produces electricity. They use all biomass. Most of it comes from the woods, but they also, about 2% of their supply is now coming from willow fields that are planted here in upstate New York. So you could put it into those kind of things. There's other things like mulch markets that have potential out there. In the longer term, we've done lots of work. I work with colleagues in chemical engineering and environmental engineering, paper and bioprocess engineering. Those folks all take wood and turn it into other things. So they've done work making biofuels, ethanol, renewable diesel, things like that. And so those are all possible, or biodegradable plastics. Those things are all possible. They have not been scaled up at any scale beyond the lab at this point in time. But you know, we're working on those to try and show the potential to make use of these wood chips for those kind of things. If we go to the next slide, I just have one or two more. So one of the things, if you're going to use these wood chips, everybody will often ask, well, isn't this material got contamination in it? So we went out and did a test. So on this table, you'll see different elements we've tested for, and we tested for a whole bunch of organic compounds as well. None of that came out as important. So Solvay is the site I've just been telling you about. Tully is our research station. That's a typical agricultural mineral soil. So the first thing I want to show you is that the ash content actually at the willow at Tully in that green box is actually higher on the mineral soil than it is in this contaminated site, as it is for a number of these other elements, right? The only elements that were higher at this Solvay site compared to a mineral soil were carbon, magnesium, and potassium. Not surprising, lots of magnesium and potassium out there, so we're picking those things up. But those ones don't have this ISO standard here is what you have for wood chips in terms of requirements to meet an ISO standard for wood chips. And so it meets all of the chemical requirements for wood chip. Next slide. I think this is maybe the last thing I just want to talk about. So where we're at now is the trial we're going to run this fall is we're going to take around 100 megagrams of chips from the site, and we're going to send it off to a pellet manufacturer that we've been working with for a number of years, and he's going to make pellets of it, and we're going to return it back. So this building is here on our campus, which is just 10 kilometers away from where these Solvay settling basins are. And in the basement of this building is our combined heat and power system. And so that picture at the bottom is the schematic that shows you that. It's a combination of uses biomass fuels and natural gas. And so the idea is that we're going to take material off this site and turn it into pellets, bring it to the site and use it here in our combined heat and power and create this loop The plan is then to take the ash that's generated out of that biomass system and put it back on the site. It's got nutrients in there that are depleted at the other site. And so taking that material back and distributing it back onto the willow fields for the next rotation to create this closed loop cycle. Yeah, I think that is, that's it. I will wrap up there in the interest of time and happy to answer questions later during the discussion.
All right, thank you. Thank you very much, Tim. That was really interesting and it's really important for us to exchange on a specific plant such as Salix and Willow, which we're actually trying and use in Biomass, even though we're trying to have a shorter coppices, we're trying to have a harvest like every year or every other year. So but we will of course investigate, and also our technical partners may have some questions afterwards in the discussion. But now it is my pleasure to move forward and discuss about hemp-based materials for housing construction and renovation with Alison Mears from the Healthy Materials Lab at Parsons School of Design. So thank you very much, Tim, for your presentation. And Alison, the floor is yours.
Thanks. We can help go to the next slide. Thanks.
Yes.
Thank you. And the next one. Great. Hi. So we established the lab in New York City in 2015. And today I'll present an introduction to the topic of material health. And Paul and Tim have already kind of touched on it a little bit, but it's foundational to our work and the way we frame our research. So I thought it would be an interesting thing for us to kind of review that a little bit. Next slide. We, like Tim and Paul, also have relationships with a number of partners, and we're funded by a grant from the JBB Foundation. Next, please. So we work with a broad range of experts exploring the relationships between human health and building materials. And for us, as we see with COVID, it's revealed the inequities of our current systems of communities that are now at compounded risk. And they're the communities that we focus on a lot in our work. Next slide, please. In our work, we consider how the design, construction, and production of our cities impacts human health and the planet throughout the ecosystem. Next, please. Construction materials in the current system impact human health through their processing, impacting the immediate fence-line neighborhoods, consuming large amounts of energy and adding significant amounts of CO2 into the environment. And this is a common theme in all of the work that we're doing. In use, which is the area that we focus on a lot, these products emit hazardous toxics into the interior and exterior environments. And so, you know, again, next slide, please. Our bad decisions have negatively impacted the entire ecosystem, ourselves and the environment as well. Next, please. Materials that are used to make our cities are becoming part of our biological systems. These materials shed and release chemicals into our environments, which are then absorbed into our bodies. Next, please. And this is the challenge. We spend most of our time indoors, and our indoor spaces are filled with invisible chemical hazards, making indoor air 3 to 5 times more toxic than polluted outdoor air. So surprisingly, in the US, many chemicals are not regulated. Only 250 of the over 85,000 chemicals currently in use are tested, and only 5 have been partially restricted by law. These chemicals are not benign, but are becoming, as I said, part of our biology. Next, please. We often think of products as static, but over time, materials break down and chemicals are released through off-gassing as dust or as chemicals become unbound and are released into the environment. Next. And these are where they enter our bodies, either through breathing them, or through eating them, or being absorbed through our skins. Next, please. So how do these chemicals in our built environment impact our health? The research study called the Exposome Project has identified that genetics determines only 10% of human diseases, with the environment accounting for the other 90%. Next, please. So the exposome measures all of the exposures, including chemical exposure in an individual in a lifetime, and how those exposures relate to health. Next, please. So the remaining 90% of disease are triggered by the social determinants of health, economic and social conditions that determine individual and group differences in health. Next. Chemical exposure is a systemic problem. A report published in 1987 by Dr. Benjamin Chavez documented the location of unregulated toxic waste sites in largely Black and Hispanic counties in the US. Dr. Chavez coined the term environmental racism to respond to the findings in the report. Next. And if we look today at where chemicals are produced in the US and where exposure and release happens, there is similarly in these same communities that we see, as what was happening 30 years ago. Next, please. And as we look at COVID locations and relate those to zip code, we see these same overlapping statistics where underserved and marginalized communities are actually more at risk of COVID than other communities. Next, please. It's critical that we build healthier and more resilient communities. Obviously, this is the object of our work. Dramatically reducing people's exposure to harmful chemicals is a public health priority and linked to this reduction of a range of human diseases. Next. So we look at how we are routinely exposed to chemicals in common building products. And these common building products release a range of hazardous chemicals into the environment, causing cancer, asthma, and impacting infertility. But in the US, it's difficult to know the content of the products we live with. Next, please. We do know what's inside of food products. Listing these ingredients is regulated, but this is not the case with building products. Next, please. So we advocate for chemical transparency so that then we know, once we know what's in a product, we can look for better choices, and then we can identify better alternatives. And so we're focusing in this presentation on this wall section. A typical US wall section contains at least 7 materials, many of which are made from petrochemicals or contain substances that are harmful to human health. That's the issue. So faced with all of these problems of chemicals in building products, we look for alternatives. And through this, we've identified this combination of industrial hemp and lime, made of hemp hurd, often considered as a waste product from hemp fiber production, water, and lime. With hemp lime, the wall section can be simplified to 3 layers, all containing the same ingredients of breathable materials. Next, please. So the benefits of hemp, and I'm sure this audience knows this, and lime are impressive. It's a better alternative to typical building materials. And we think that this material has the potential to make systemic change in a range of industries. Next, please. And I, like Paul, love these systems diagrams. And so as we think about the use of this crop and lime, we think about how we can create these beneficial systems. So industrial hemp is a new crop in the US, and it was legalized in 2018. So there's a lot of knowledge that needs to be accumulated in this agricultural part of the system that we're looking at here. Also, the way that it binds with lime also needs to be explored. And we think then with this combination of these 2 ingredients, we can start to imagine this new system that combines these 2 ingredients into better building products. Next, please. So we began this process. We've been researching hemp and lime for the last 2 years or so. In January 2020, we started to bring in students from Parsons to look at the implications of kind of innovation and practice implications. And we began with just making hemp and lime in a workshop in January in 2020. Next, please. So architecture students, as you may know, have seldom had the opportunity to actually have hands-on experience and work at full scale. So this was a great kind of introduction to a studio where they could start to look at the physical properties of hemp and lime, the mixing of them, the sensorial qualities of them, and the limitations of them. And so they did both cast walls and also looked at some block making. Next, please. So we center our work also in areas that have been suffering, well, typically a lot of post-industrial cities in the US, so similar to what Tim is looking at in the north of New York State. So in Newcastle's a city in Western Pennsylvania that has gone through this deindustrialized process and has, a number of abandoned timber balloon frame houses. Next, please. Our partner in this effort in Newcastle is Dawn Services, and they're an affordable housing provider, particularly focused on accessibility. And they share this vision with us that hemp line buildings and the whole system that fuels them could be a huge opportunity for both Newcastle and the development of new affordable housing construction and renovation protocols. Next, please. So the Masters of Architecture students went through this design process of actually looking and comparing what it might mean to transform an industry from this petrochemically based wall system to working with a new system of hemp line, and particularly focusing on renovation versus new construction cost. And you see here the savings associated with renovation, this 43% saving with renovation. And that's also not only saving in dollars, but it's also savings in carbon emissions. We also looked, next please, at the goal of scaling up hemp line construction and how it could contribute, it could participate in a traditional construction sequence, and looking at how, if we used precast hemp line components, we could accelerate the construction process. Next, please. The students were allocated sites in Newcastle, 15 sites, 15 students, and asked to consider the future of the American home, both in terms of new construction and renovation. Next, please. And came up with a variety of different design responses to the site, the city, and using this material. So this for us is very important. We want to really explore the design opportunities that are available if we were using this product. Next, please. So this proposal, called House with Two Porches, was proposed by Samuel Wilson. He creates a very simple form. You can see him exploring the wall section there, which is obviously the focus of the studio. But he was also interested in this new American house, how we could account for a variety of different family groups, and how we could work on kind of any site. Next slide, please. Merrill Smith's rafter house takes the ubiquitous roofline shape of American houses, extrudes it along its narrow site and creates a generous outdoor space that is fully accessible. Next, please. So this was a semester full of obviously disruptions, but also a semester of many insights. And we continued at the end of the semester our collaboration with Dawn Services, and in particular looking to renovate a wooden balloon frame house in Newcastle with hemp line as a prototype for the future. So next, please. So we know that it's not just the adoption of a new building material that is required to make change, but it really needs to be, we need to create a new agricultural system, new industries, build the workforce, and reduce, obviously, and sequester carbon. So back to this diagram. So with these examples and all the work around the country, there's some great progress happening in the US, but how close are we to bringing this whole system to fruition? And what are the roadblocks? Next, please. So first of all, we looked at agriculture, and this affordable housing organization is amazing. They wanted to look at, whether they could cultivate their own hemp. So they're looking at that, the beginning of the system in agriculture. Next, please. So in the summer of 2020, they planted 14 acres of fiber hemp in 4 counties. And they experimented again, as Tim was saying with his WILLOW project, only choose seed varieties. They hope to get 4, but just access to seeds is very difficult. And they tested a number of planting methods to see what was most successful. They had a good season. Next, please. They were able to take the harvest, and working with a local innovative material producer, they're taking some of their harvest and incorporating into this new hemp wood product, which has some viability and interest, and that will be used in this next project that we're working on, which is the Pennsylvania hemp house. So using this very small, simple house as potentially a demonstration about the viability of incorporating hemp lime. So using hemp lime in a structure like this would introduce energy efficiency. It would make the structure, the wooden structure, flame resistant, and it would create this healthier indoor environment, this breathable wall for the future owners. And this is the challenge. Next slide. Typically these wooden framed houses are really susceptible to fire. So this new product would help overcome that problem. Next, please. So currently in the US, hemp hurd and lime binders are imported from Europe, which is crazy. Paul talked about this, we need to create local industries. So how do we accelerate this production of local lime mixes to combine with locally produced herd to advance our goals? Next, please. So another colleague and partner in the Newcastle project, Cameron McEnroe, is exploring a number of different techniques. One is this blown techniques. He uses a hemp lime spray to insulate an existing stone wall. He's also working on creating a lime binder made from limestone found in New York and Pennsylvania. So we know that hemp lime blocks are produced in Europe. Next, sorry, Pietro. Yeah, and they offer examples of accelerating installation and construction. Next, please. And we've been involved in local production of hemp lime too in factories in Pennsylvania, first in Eastern Pennsylvania and more recently exploring it in Western Pennsylvania near Newcastle. Next, please. And finally, one of the final hurdles to overcome is to convince local building codes to change their codes to be able to incorporate a new product like hemp lime. And creating a full-scale mock-up like this allows local code officials to understand exactly what the physical properties are and the manifestation of this new product is in a kind of reality. And that will help, we hope, overcome some of their concerns for this product. Next, please. So we're excited about this potential for Newcastle to prototype hemp lime affordable housing. We think that it might be a prescription for the future, for renovating many of the abandoned houses in the Northeast and Midwest, for renovating housing to be healthier, affordable, and made from locally sourced materials that invigorate local economies. Next, please. We have a booklet that we've created that kind of explains a lot of our research to date, and you can download that from our site if you're interested. And we also have a podcast focused on, the first season was focused on hemp, we're excited about. So take a listen, Trace Material, wherever you find your podcasts. We also believe in open sourcing, as I'm sure all of our partners here do. And if you go to healthymaterialslab.org, you'll find a bunch of resources. And I just emailed Paul this morning, the woman who manages our materials collection, and told her to look out for Hunex as a possible material to put on our website. Thanks very much.
Thank you. Thank you very much, Alison. That was really an interesting presentation, and also touching on the topic of environmental justice and injustice and inequalities. I think it's really key to find affordable solutions to, especially in Romania, for instance, we have the issues with retrofitting poorly isolated materials, and this would be absolutely a cheap and feasible solution. And I think it's a kind of a common topic, the usability, the versatility of materials that would contribute this quest for better housing for all. And so now I would open the discussion, and first I would suggest that our UAA expert, Amaya Selaya, which I see is here, if she wants to have a reaction on the presentation she was able to see, I would very much welcome her contribution, and then otherwise I would open the discussion to the audience. We already have a couple of questions from the chat box. So, and then Amaya, chat box questions, and then please raise your hands, and I will give you the floor.
No, I want to give thanks to all the contributors to the webinar. Exciting and super challenging projects. I think that this is an adventure we are living all together, because you have been very transparent, not only showing your outcomes, but also your challenges and your difficulties through the processes. And with this Via Mare now SPIRE project, we are now living in difficulties and in challenges that we need to overcome. So I think this is it. We are all together, and we have to keep thinking together about how to solve the problems that are not solved yet, as for technology and processes, users, industry, etc. So that's it. Thanks. Over.
Thank you, Maya. Yeah, I see it like the next step is, say, like the scalability, the usability, so finding a way from the experimentation to the actual mainstreaming of the materials, but I think this will be the objective of everyone works here. We're just experimenting and trying to get to something that will stay and inform the future of constructions and urban development, housing development. I wanted to read a couple of questions that we got from the chat box, and the first one is for Tim. And it would be if you can tell us what other uses are there for the willow plant besides energy, because you were mentioning basket making and other applications. And so this question is for you.
Right. So people have done a lot of different things with willow. So there's interest recently that's occurred in the mulch market, and there's things in the chemistry of willow that appear to make it a much more effective mulch than some other wood mulches that are being used. So there's one. People have used, and there's folks in the area and also in Quebec that are doing work on making living walls. So outside living walls and sound barriers using willow. People are putting willow into, you can make brown papers and cardboards out of willow. It's a hardwood. The challenge is you can't get the bark off it very easily, and so you're not going to make white paper products out of it very easily. So there's a number of different applications that people have used looking at willow. On the chemistry side, there's a whole lot of people in the medical field looking at extractives from willow. And that's not my field, but I know there's a lot of work being done on that and some of the chemicals that are in willow and using them for different applications in the health field as well.
Thank you, Tim. And I would raise another question from my side. That is, of course, we are experimenting in a very highly contaminated territory on soils that are contaminated with heavy metals, especially lead and copper. So, of course, there would be limitations in using such materials in applications that are getting in contact with humans. So, what can we actually do when using willow, hemp, or other sort of paper mill waste in the using of materials in constructions? Can we use them to build insulation panels, for instance, for housing? Do we need to make insulation for these insulation panels in order to make them usable into housing? Are we able to use them to burn the chops and the pellets without further harm? Like, this is broad question on potential side effects of the reuse of biomass in a contaminated land from contaminated soils.
So I'll comment on, I think one of the first key things on any of these sites where you work on is you need to do some assessment of what is actually in the material, right? So for willow, different willow species will take up different amounts. We've just finished some work dealing with cadmium contaminated sites, and the plants don't store a lot of that cadmium in their wood structure, right? It's in the roots and it's in the leaves, and the levels in the wood are relatively small. And so in terms of the concern about what we were going to do with the wood afterwards on these sites was relatively low. It's going to be different. Lead is going to have a different, it's going to end up in different parts of the plant, for example, than I think cadmium would. But the site is also going to have an impact. So you really want to do an assessment of some material harvested off of the site and to see what levels you're dealing with, and then make some decisions. If you're going to, other people can comment here that are doing building materials, but if you're going to put it into a building material and it's going to stay in a more fixed form, then I think in terms of a lot of those heavy metals are going to bound up in the cell wall structure, and you're not really going to have as big an issue with concerns about release. But certainly, if you're going to use it for energy, you want to assess it and make sure that it's not going to have problems. If you have proper control, like our system here on campus has an electrostatic precipitator, and so our emissions are very, very small. We're in the middle of an urban environment, so we put that technology in. It's going to end up in the ash, is where most of those metals are going to end up, if there are any. But as I showed you, at this Solvay site, there's not a lot of metals in that material.
Yeah, sure.
So testing is the key to understanding in it.
And I understand that needs to be done on soil, on field, and not in the greenhouse, because of course results are going to be different dramatically. And so this is what we're trying to do in our pilot sites. Alison or Paul, do you want to add anything?
I would just say that one thing, sometimes if you embed it in a building, whatever that chemical is, whatever that poison is, that that it's sequestered there and then it's safe. But the interesting thing about hemp lime, the material that is made into this kind of insulation wall section, is that at end of life, you can break the wall apart and collect all of that hemp and lime material and add water, and you could take it back to the factory to make concrete block, or you can cast it again in situ. And so that through that process, which is kind of amazing, right? So it's a truly circular building material. But through that process of, demolition and reuse, which is seamless, you may find, to Tim's point, that some of those chemicals become unbound through that process. I don't know, but the testing is hugely important, I think.
Right, thank you. Paul?
Yeah, I do agree actually with what Alison just said. Now, to us, our experience, the waste we're using has really low percentage of heavy metals. It has some due to the inks contained in paper, but in order to ensure it could be used in the product, we've undergone several tests, as Timothy said, and as in the raw material as well as in the final product. We've not seen from a regulation point of view a limitation on those. Obviously we have really few. We followed always the call-to-product criteria. In our case, what we did was ensure that all the specs of the material and all the composition it has, all the elements, meets the criteria to achieve in our case, the material health silver certificate.
Right, thank you. And then we have a further question from the chat box. That's another question for Alison, and says, in your research, are you aware of other plants that can be used for isolation similarly to hemp?
Yes, so Chris Magwood in Canada, if anyone wants to look him up, has been looking at a range of different materials, plant materials that have a similar stalk structure as hemp. Actually, my colleague John Sarah Ruth is on this call, can explain that, but there's a cellulose structure, I believe, and in the way that the moisture moves up the stem, that you're looking for plants that have that similar kind of structure. It's that structure that allows the plant material to bind to the lime. So he's been doing some experiments with sunflower, I think, and some other crops. So yes, there is interest in looking at agricultural waste more broadly, so that you can do kind of regional building. So if you could perhaps overcome some of the regulatory problems with industrial hemp. There are still issues across the world with growing this plant, and look at plants that are more generally available. So yeah, there are people doing that, and Chris is a great resource for that kind of information.
Great, thank you. So I would probably ask if there are other questions in the audience. Otherwise, I would ask for a question that was raised at the very beginning. That is this difference and need to merge between the usability of our materials against the coolness and the hype that there is behind such new materials. So if we have also someone in the audience who's actually on the practitioner side, that is either a designer or a worker in the construction field, that can tell their experience in using these materials, or even if our guest can comment on how they perceive the adoption of such materials in construction in real life. Because of course, one of the aspects in our project would also be that of financing, and sorry, not financing, but supporting local startups that would be called to produce such materials and then put them into use. So what would be your experiences in this? So if we have any practitioners from the audience, otherwise I will go to the speakers, starting from Alice and Tim and Paul.
The question is around adoption. We didn't have any raised hands, right?
I haven't seen any.
In construction, and we've talked about this a little bit, it's a very conservative industry. So making any kind of change to incorporate a new material that is untested in terms of not being in use for any length of time is tricky. And so for us, that's why we prototype and demonstrate, and that the project for us in Newcastle is hugely important so that we can do the testing, do all the interior air quality testing, the flame retardant testing, the structural in terms of the integrity of the wall to ensure that it stands up to kind of common use, the insulatory quality, all of those things, so that it can, and then, you know, follow-up testing in terms of long-term use, so that we can demonstrate that this is a viable alternative. That's the hurdle I think we're facing right now. It's great for us to work in the laboratory, or for us to have a good idea, or for it to look cool, but you know, if it doesn't perform in regular practice, people just won't adopt it, or the only people who will adopt it are the people who can afford it and are interested in doing something cool, and that's for us not an interesting place to be working. We want large-scale adoption.
Right. But of course, I mean, I think our really best option would be to have such materials that we can actually use, especially to insulate plants, and the dimension of having the production local and use it in the local level would be a key to overcome a lot of injustice. So maybe we have some comments from the audience, or from maybe Amaya.
Petra, this is Jane. Oh, sorry, I'll just jump in and comment really quickly.
Hi, Jane.
Good morning. I am an interior designer in Pittsburgh, Pennsylvania, so really close to the location that Allison has been speaking about. Here in Pittsburgh, as our transition from the industrial culture has really created a sense of a maker community. So we have a lot of woodworkers, some ceramicists, and that aspect of our local culture is really celebrated. And we really try to encourage this a lot in architecture and design. And so what we try to do in our practice is to incorporate local makers into our designs wherever possible. And we feel that that helps create a stronger sense of place with our workplace clients, that they're celebrating the local makers and supplies that are being created in their area. And so that's really an opportunity that I see for especially the hemp industry in Western Pennsylvania, is that there is a really strong pride. If anyone's ever seen a Pittsburgh sports game, that Pittsburgh loves to celebrate Pittsburgh. And we're really excited about all of the opportunities that this area has created, and really to celebrate that that research and all of these products that are being made. And so we'll sometimes use some of these products that may not have the same durability as a really stronger commercial heavy use product, and use them in smaller special places first to get our clients more familiar with how these products might look or might work. Also to help kind of offset the increased costs that some of these might have, because a lot of these products are literally being made by hand. And we've found that to be extremely successful in our workplace practice here in Pittsburgh.
Fantastic.
Thank you.
Fantastic. Thank you, Jane. Amaya, you wanted to say something?
Well, I was going to say that I am not totally sure I am being a reference, because I have been teaching about materials for years. So I always try to use, of course, as all of us, I think, this kind of materials in my work. But I remember 10 years ago, at least in Spain, north of Spain, Catalonia now, we began to work with cork for insulation. At that moment was, oh my God, we are going to work with cork. And it was a material of proximity. It was just 50 kilometers from our field of work. And we got just using cork, among other measures, a nearly zero building. And the practice became like the normal. And now you have several events of nearly zero buildings in the Mediterranean that have been built with cork. So I think it's just, we have to begin. And then everything is going to happen, because we need to speed the process, and we are very late. So I have this hope of that. Yes, the speed will come because we are really in need of doing it, but we need to make the first step.
Any reactions from our panelists, or maybe Kudrut has some question afterwards?
I would like to add just, following what Maya and Alison and actually Jane said, it's important. At the very beginning, especially when you have a new material, the first thing you have from an industrial point of view is that you have a very small production capacity, because you're just price competitive when you have a large scale production. So in the beginning, you don't. That also means selecting your clients, but especially the ones who transform the material, because as Alison perfectly said, it's the carpenters or the typical industrial carpenters, they are reluctant to change, even to the slightest change. And that means that when they get a material, even before trying it, they say it will not work. At the very end, it takes them maybe a couple iterations to make it work. So it tends to be easy, because when you develop a material, you develop it to be competitive against a certain material that is in the market. So that means that the way it's transformed, it's going to be pretty similar. It may have you may need to adapt it a bit, but not much. So choosing, to me, at Honex, the most important thing has been to actually choose which industrial partners we want to work with and just work with them. Because we don't need to sell millions of square meters, but what we need to do is ensure that every square meter of Honex that is installed has the highest quality. Because by achieving that, we will be able to improve the material, because obviously everything, when you release something, it's a better product and it needs to be improved. And when we have a larger scale production, also smaller, lower prices, we will be able then to face all the conservative industrials, but we will also face them with so much experience on how to transform the material that they're questions that now require a lot of effort to work together with them. And it's mainly time. They need you to be by their side, help them transforming. And it's maybe to us, it's not the timing right now, but with some years experience, we will be able to summarize all that in a transformation book, and then you become a mass market material with it. So it's about that. Everything has a timing in the beginning. Choose the right players or to work with.
That would be the hardest part, to choose the right players. Kudrut, do you want to chip in on?
Yeah, I have a question for Tim. I want to ask you, how many hectares of willow is used for heating the campus building? How much is needed in order to be sustainable?
Right, so we're not running the biomass. Right now, we're using about 250 tons a year, and it's underutilized, right? We could use up to 2,000 tons, but natural gas is cheaper. So in the current financial crisis we're in, we're going to use natural gas first before biomass. So how many acres? So for that 250 tons, we'd need maybe 20 hectares or so.
Okay.
Yep, you'd have to scale it. You want to scale it to the size of your system. So one of the other uses, there's a building on site, literally a couple hundred meters from where this willow is growing on this site, where they're treating leachate that's being collected, leaking out of the bottom of some of these other settling basins. And so one of the other things that we're exploring, although it's not as far along, is to put a chip heating system for that building. And I think for that building, that wastewater treatment building on site, the estimates are it would take about somewhere between 10 and 15 hectares of that willow just to heat that building. But it'll depend upon the size of your building, right, and the demand that's there.
Okay, I was asking because we want to heat a school, and we have a total of almost 7 hectares of land, and not only willow. And I think it's important to assess this, to see how much willow we need to heat a school gym.
Yeah, so we could fairly easily make a rough estimate of the yield, what the energy content is, whether you're going to dry material, use it wet, what the energy content would be, and then what kind of heat that might generate. That would not be that difficult to do it, at least at a high level, right? And then you can look at what the heat demand is that school based on vast experience and see how they match up. The other thing with Willow is, you can use any, it works just like any hardwood forest residue material. So I often advocate for people that want to do projects that, if it meets the majority of your need, or, that's fine. It doesn't have to meet all of it. You can use other wood resources, right, and have a blended supply to provide stability. There was a school in Pennsylvania that grew about 20 hectares of willow, and it probably met about 70% of their supply. But then they had times when they couldn't get on fields because they were wet, but they just replaced it with forest residues and changed the mix somewhat.
Interesting. Thank you.
Thank you. Thank you.
So I just wanted to comment on this last discussion. I think one of the key things is involving people early on. So I'm an advocate, and I advocated in the project that I talked about that early on we should have the community come, and early on we should have the regulators come, and we should open it up for discussion. Now, I'll tell you that some of the company in particular I was working with didn't think that was such a good idea, right? They wanted to get it all perfectly packaged and working before they went to regulators or the community. But in essence, there were lots of questions in the community, and I think we did much better by opening it up early on and saying, hey, look, this didn't work, this worked, this is how we're gonna move forward. And I think we built confidence along the way. So I think doing that, Allison's example of these wall panels so that inspectors can come and look at them, those kind of things make a huge difference. When we started with regulators, all they knew was clay caps and geomembrane caps. That's standard procedure, right? Nowhere's in their regulation was willow or any evapotranspiration cap in their regulations, right? So we had to walk along with them, much like you need to convince them that these wall panels are going to meet all the sorts of criteria that are required, right? And Paul, all the testing you've done with, fire resistance, all those criteria that are important, right? I think it's important to do that along the way and bring people with you and answer the questions people have early on. If you wait to the end and then get those questions, you got to go back and fix them.
Yeah, absolutely. Building confidence and advocating and building critical mass around this innovation is absolutely crucial to get it accepted and used and mainstreamed. And of course, like with hemp, there's going to be major problems because of the stigma it brings along with, even though totally unjustified. Because of course we're talking about somehow a different plant with different property, but just the leaves look the same way, and that's the major problem we are facing. For instance, in Romania, we really are blocked on this side. But of course, showing what is possible and there's no harm on this, I think is going to be really key for us. So I thank you very much for showing examples of how things can be done successfully all across the world, I would say. So I would say, just if you want to say a last word, and then I would just present the next conferences. So if Alison, Paul, or Tim want to say the last word.
I would reiterate working with partners and with community and kind of drawing from the knowledge of everyone who is interested in making change that can accelerate the work in ways that are kind of unimaginable. So I'm excited always about working with others. Thank you for inviting me.
Thank you, Alison, for joining us so early in the morning, as well for Tim.
I'll just say one last thing related to that. I often tell people that we can figure out the technology and we can figure out the biology, right? In our system, we often don't spend enough time on the sociology and psychology, right? And I think a lot of systems don't move to that next level because we forget the people factor. And I'm a strong advocate, although it's certainly not my training and background, that, we need to spend more time. This is where I rely on colleagues, right, to provide input and guide us. Because if you don't work with the people along every system we've talked about involves people, lots of people at different stages, regulators, end users, manufacturers, people building things, right, or using energy. It's all people, right, and they all need to make a decision to buy into your idea. So I think we need to spend a little more time on the people part, and we'll get the technology and the biology pieces figured out as well.
Great, thank you, Tim. Paul, you have one last word?
And I think not much to add to what Alison and Tim have said. I mean, actually, as Tim said, sometimes it's more. I mean, it's more critical people than technology. Technology can improve. I mean,
yeah, more skeptical on people then. Joking, of course. All right, thank you very much for all our guests for joining us, especially for Tim and Alison from very early in the morning in the US, from Paul from Barcelona, and Amaya as well from Barcelona, as well for the other participants and an audience that join us today. I thank you very much for being here with us today, and I would also invite you to the next webinars we are carrying out. The next one is supposed to be on the 8th of December, and we will be discussing on reclaiming polluted brownfields through phytoremediation. So this will be a more technical webinar, and of course, you are all invited to join. And then we are planning another final webinar in 2021 about building new green digital economy with blockchain for future climate neutral cities. So I thank you very much again for being with us. I'm looking forward to seeing you at our next webinars. And of course, we had a technical problem on sharing on live streaming today, but the registration will be made available through our Facebook page on SPIRE by Amare, as well as on our YouTube channel, which is again SPIRE by Amare. And then of course I will send to all our speakers and panelists the registration, the link to the recording via email. So thank you very much, and wishing you all a great day, and see you soon. Bye-bye.
Bye-bye.
Thanks. Bye.
Thank you.
Thank you all.